What I'd like to describe are the basics of our technology, which consists of taking an oxygen sensing dye, or it's almost like a pigment, which I have a bottle here. This is mixed with polymer, raw resin, and this can be compounded together in standard manufacturing practices for making master batches for then extrusion into thin film laminates. But I've got an example here of two different dyes that I'm showing you. They are distinctively different colors. They're different oxygen sensing compounds which we've selected for their different properties, and each has been introduced, as I call it, at least a small example of a master batch, where it is by melt process mixed with polymer. And then, as I was referring to, the polymer can be extruded into rolls of thin film, multi-layer laminates, barrier films, etc. This is one example, and we have many other examples, of which here's some samples of materials that have been made into a pouch, sealed pouches for some test purposes. Here's one actually showing like a bag as an application of a oxygen sensing film, and I'll give a demonstration of that in a minute. But these materials that are oxygen sensing, I wanted to show exactly what they can do by virtue of a demonstration using, I'll just use a black light. We are typically measuring the oxygen with a meter. I will give you an example whereby the oxygen is going to be modulated with just a nitrogen stream under a black light. I think that will give a good representation of the nature of the responsivity of the material and how it is reversible, going back from a response of luminescence in a low oxygen and a high oxygen form. So we'll take a break and I will get the UV light out and give you that demonstration. I wanted to show you a quick demonstration of properties of the luminescence of this material. Here I've got a UV laser, more in the way of the blue spectrum. Shows the red emission that occurs from the dye itself. And I'll now, with these two polymer mixes, master batches, here's one, here's the other. You can see the red emission from them, and in a thin film form that I've got a little square of here with quite a bit of dye in it, just so that you can at least see for the visual demonstration about the red emission that is occurring with the stimulation of the dye by this particular laser light. And this is these are some little dots that we've made that are oxygen sensing, and we have another one over here, which this is a different material, different type of application where it's sensitive to a very low level of oxygen and air. There's not much of a response to it at all. For a quick demonstration, I'm going to show you now this other matrix that's coated with the thin layer of the oxygen sensing dye. And we'll turn the lights off, and under ultraviolet you can see there's a little background fluorescence to this particular material, which I wanted to show the modulation. As I blow from this tubing stream of pure nitrogen gas across the polymer, and you can just see the change, the increase in the luminescence and in the phosphorescence or lifetime of the dye as it's responding to the low oxygen. And then as you move away from the nitrogen stream, the oxygen quenches the dye and causes it to go back to a relatively lifeless or non-fluorescent form. So that's a quick demonstration of that particular material. But we've got another, I wanted to show you this film here, which, if you can barely see it, it's not even in the presence of air having any response at all. I'll blow the nitrogen at it, and there's enough air that's mixing with the oxygen at 21%, even despite the pure nitrogen stream, you don't see much of a modulation in it. But if I take and put this, let's say this was a package of this film, and I had the package then purged with nitrogen, as in a modified atmosphere type of application, you can see where the whole sensor dot, or film actually in this case, is getting brighter due to the displacement of the oxygen by the nitrogen in our little test chamber here. Now, as it has responded to a low oxygen environment, if the package had a leak or a breach in it, hole, and the oxygen is allowed to get into the inside of the package, the response is going to die away just like that. Okay, one other application for something in a film type form would be in the liner of a cap to a bottle or some other container or vessel, having a cap or a closure. I've got three bottles right here. One has no liner in it. This one has an oxygen sensing liner that has been exposed to air, and this one has been exposed to low oxygen through a nitrogen purge. Actually, you can see that that's reversed. I was wrong. We put them up there in the wrong order. You can easily tell now under the black light where you can see all three of them simultaneously. This bright one here is the low oxygen, and this is the normal air. And I believe we could even further demonstrate that if I was to take this one and we introduce some air into the package, sensor response to it, you'll see that the luminescence wanes away and it will go to match the one that's the ambient air. Okay, so that's a series of demonstrations just from a visual standpoint that gives you a feel for the responsivity, different levels of oxygen that can be measured, and a couple of the types of applications that we can utilize with this technology. Having given you some visual demonstrations of the responsivity of films and different configurations that we've created, I want to now show you indeed how the films can perform as we analyze with our instrumentation here with the optical reading of, I've got a particular film here that's, you can't even see the oxygen sensing dye that's contained within this polymer. It's a multi-layer laminate, but I have a sample here of that created into a pouch that's sealed and has been filled with nitrogen gas, and we're doing a measurement of it right now. Over here on my computer screen you can see that we're tracking the oxygen on a 10-second interval, doing updates here of the measurements. I'll explain in a minute, but indeed we've got like a 0.7% oxygen in the environment as measured with the system. What the system consists of, well, what I'm going to do first is I'm going to take and remove the tape that's covering the hole on the bag, and that's where the nitrogen was injected into the bag. We'll just let it sit there and leave it for a couple of minutes, and we'll look at the change then as measured by the oxygen, our oxygen sensing system. This is a LED over here on this side of the instrument, and up in this portion at the top is a photodetector. We are projecting light onto the surface of the package. It is from the emission, the red emission is being picked up by the optical head, and the lifetime is being calculated of the signal after the LED light is actually turned off, and this LED is going off and on doing a repetitive flash measurements of the surface of the package like 1,000 times a second. So we're getting a outgassing of the package and some oxygen going into the package. I've got another film material here, one that I showed you earlier, which would be this one's a little more easily seen perhaps with the red color in it. And I had demonstrated that under the ultraviolet light. We're already seeing, since I removed the tape, the effect of oxygen going into the package. I'll allow the camera here to take a view that you can see the oxygen signal. Oh, there we go. Hello, Windows. The signature is going up here. This is where we had our measurements going on before I took the tape off the hole, and now this is the signal showing an increase in oxygen. Actually, what we're seeing, the instrument is detecting a decrease in the lifetime of the emitted signal from our oxygen sensing dye. This application of what you see was with earlier instrumentation, of which we have this now reduced to a small footprint here. On this board we actually have 4 independent oxygen readers present. Wanted to show this to demonstrate that we think it's entirely practical and feasible to ultimately have just a little handheld portable type scanner like you would see in your warehouses and grocery stores and so forth now for doing barcode reading and other types of handheld scanning. Quite practical even to have wireless technology with today, being able to take signal and transmit it anywhere in the world to do your tracking of package integrity. This technology being able to monitor quality of packages both from a map standpoint, and the same is really true with vacuum as well. Vacuum simply being a way to reduce the oxygen tension. When the vacuum is lost due to a breach in package or loss of integrity, the oxygen is going to go up in the package, and the sensor material inside the package is going to be able to track that. Our signal over here now is showing a couple of % oxygen. It's been continuously monitoring this trend line of the oxygen going up inside the package, which is really quite remarkable. In particular, if I might emphasize the point that the reader does not have to be up against the package in direct contact with it. We've perfected this to the point where you can be reading off of the package, an offset of several inches here actually between the surface being measured and our optical instrument, giving one a great deal of latitude as to how the reading is conducted. And in an automated manner, the reader could be sitting under the package or over it, as we have here, as packages move underneath, if you had say an automated line that you were wanting to do your package scanning on. So there's the demonstration of proof of concept and feasibility of the reading technology, and I'd like to next talk about the various modes and applications, still some other renditions of using the oxygen sensing material. I wanted to talk briefly about the various kinds of applications that we know or have already had some experience in implementing, and I wanted to make a mention first of the pouch, flexible bag, and the polymer material. For one thing, in that demonstration done earlier, this is just a piece of foam rubber that's been put in the bag for our test purposes, so that when we put the needle into the bag, we didn't puncture a hole clear through the bag on both sides, and only got into it enough to put the nitrogen purge into the bag, or the nitrogen flush. The application of the pouch, I should think, is obvious from this. With a flexible film, the concept certainly is applicable to a tray as the lidding material shown here. In addition to being the top lidding is a sensory film, the inside of the tray itself could be lined with an oxygen sensing material, a film. A tray as well could have, for instance, a discrete oxygen sensing material that's that's put into it. Here would be, for instance, a bag where the whole bag could be an oxygen sensor. In this application as well, introduces the fact that the cap could be the means to sense the oxygen, or it can even be incorporated into such as the fitment, the attachment here. Any place that you can, in fact, imagine having a polymer introduced as a layer or a coating, or otherwise physically adapted into the material. Another one that's maybe a little more on the obscure side would be, in addition to the tray, the actual lidding material here has a polymer layer on it that you can make into an oxygen sensing layer, and when this is sealed up, you can do measurement then from underneath. When you've got a tray like this that's transparent, then you can make a reading off of the lidding of that. Blister packs, again, that would either be a candidate for into the polymer of the tray itself or the lidding material. Speaking of lidding material, I thought I would bring this out as just one to make a demonstration and a point of the fact that colored material is not necessarily going to be a barrier to utilization. We have sensed the oxygen sensing dye through colored or pigmented polymers. It depends upon the color. Continuing with my examples here, here I have a couple of trays. In this particular case, the tray itself again could be oxygen sensing, or you could have a lid for the product that's oxygen sensing. And we have done other things as well on the oxygen sensing aspect of converting. For instance, this is a filter. It's got a porous element inside that we turned into oxygen sensing material, so that the whole device now is an active sensor as well as a filtering device for biological applications. And we've done an application of putting the oxygen sensing layer, if you want to call it, onto a cork for reading bottles. So that's a cadre of the diverse things that can be done using the oxygen sensing polymer and our technology, in particular with various types of extrusion and lamination processes that are amenable to current packaging practices. And I think that gives a good coverage. Oh, I did forget the little spots as well, or the dots as we call them, that in a particular rendition could be put into packages as discrete sensors applied anywhere in or on the edge of the package, for instance. And one other thing of interest is that, in particular with a heat-sealed material, given the nature of our technology, you can measure and you could be able to determine when you've got an integral seal based upon the sealing properties of the oxygen sensing layer being bonded, thermally bonded to another material. We believe that it's possible to measure that optically and thereby make a determination of the integrity of the material, the whole packaging seal. I'd like to make some summary statements about the smart packaging technology that I've shown you today, and point out the real value added. Just summarizing some of the aspects of what we have here in retrospect is the technology for doing low oxygen sensing down all the way into the parts per billion or lower. High oxygen sensing up to essentially 100%. Measuring oxygen in packages in a situation where you have gaseous state oxygen, as in a dry environment or the headspace of a package, or in the dissolved oxygen of a liquid or a beverage within a container. A technology that's applicable to either the field of vacuum as a route to low oxygen, or modified atmosphere, the MAP packaging, for any designed package environment, and one in which we can implement the sensing technology for reading packages that, as in pouches and trays, to bags, could be large containers, vessels of hundreds of gallons, or quite literally we can measure in very small, call it a vessel or a container, and measure quantities of no more than fractions of a mil. And we think that this technology is really quite valuable. I'm going to show an example here of a situation to where, for in the general aspects of being able to measure the quality of the environment in a package, such as MAP, or the integrity of the package, such as through vacuum and checking of seals and seal integrity, that this really has a great deal of utility for not just doing sampling of a small percentage of packages coming off of a packaging line. What we're trying to convey is here's the route to being able to do 100% QC, and QC going not just from the plant where the package is produced, but all the way out, extending into the field, and frankly up to the point of use or sale or customer usage, which can be extremely valuable, say in a medical or in an electronics industry, where the quality of the package means everything to the quality of the contents. And I have a package here that, for instance, as I've shown you by example earlier, could represent that this was an oxygen sensing film. If you looked at it, you'd have no way of knowing whether or not this package had integrity or not. I can assure you it does not. And if we had our sensor in the package here, we would be able to confirm that, frankly, I think this product is actually quite spoiled at this point in time, unfortunately. But we, having introduced that, I will additionally say that we think that the opportunity to be able to detect contamination and spoilage of product has to be as well considered as one of the real features to this approach, so that in addition to measuring the oxygen environment and realizing it's in spec from a packaging standpoint or out of spec, the out of spec measurement could tell you, in fact, if the product has become contaminated with bacteria and has growth in it and is a real hazard or risk to the consumer. The efficiencies that are going to be offered to the packager are going to range from the reduced cost of operations at the line for both sampling, as well as reduced loss potentially of product when the equipment, packaging equipment, goes out of spec. Being able to identify those kinds of changes or errors in equipment and faulty operations or processes, and net reduction in the losses from your out-of-spec packages in the packaging line has got to be of interest to your package customers. And the increase in customer loyalty from knowing that they have product that is going to allow a higher level of quality control has got to be an advantage as well. There's reduction in the risk of the brand image and loss of reputation from flawed product entering the marketplace, and generally in terms of lower liability risks. These are going to include the reduction in the flaws, as well as opportunity to avoid such things as bioterrorism attempts and adulteration or tampering of product. It's going to provide opportunity for premium pricing commensurate with the higher quality and the safety that's offered by the package materials. I'll point out that as well, that one of the things that this technology can do is that the package that doesn't really have a classic head space, we can make measurements in it that is need by other invasive techniques to have a headspace, and you simply may not have that available in certain kinds of products, and we can measure those despite there being no real headspace volume. For the customer, the increase in confidence in their suppliers is as well going to be a real advantage, and the reduced loss that they know by being able to have the assurance that there are no inferior products or unusable product that they're going to have to accept, and being able to, in the field, using such as the handheld type of instrumentation, be able to do checks on product or master bag products, and assure that the integrity is there, both from the standpoint of how it was packaged as well as how it was shipped, treated, and handled, which would include shipment overseas, for instance, and knowing that in addition to other things there hasn't been an invasion or tampering of product. Lower liabilities is going to be of a real advantage and interest to the customer. And I think that in summary, we are presenting here a game-changing technology for raising the standard of package quality, package efficiency, and safety. Thank you very much for listening to our presentation.